Hi, I'm Dr. Incognito. In this video, we're going to discuss related rates. Suppose we have a situation where we have a circle, and that circle is, say, growing. Maybe a rock has been dropped into a pond, and this is a ripple wave caused by the rock. So we have a circle of radius r, and the area of the circle is pi times the radius squared. So we have a relationship here between area and radius. The question is, suppose we know how fast the radius of this circle is growing, then can we figure out how fast the radius of the, can we figure out how fast the area of the circle is growing? So that's the idea of related rates. If A and R are related to each other, and they are through this equation, then perhaps the rate at which they are growing is related as well. So in this situation, the circle is growing, so the area and the radius are not constant. We will say that the area and the radius are functions of time. They're functions of time. Then the symbol dA dt would tell us the rate of change of the area with respect to time. That's how fast the area is growing. And the symbol dr dt is the rate of change of the radius. That's how fast the radius is growing with respect to time. So A and R are related by this equation here. And so we expect that dA dt and dr dt will be related as well. So A and R are functions of time. To discover the relationship between these rates of change, dA dt and dr dt, we use implicit differentiation, and we differentiate both sides of the equation area equals pi r squared. We differentiate both sides with respect to the independent variable t. R is a function of t, and A is a function of t. So on the left side, this can be condensed as simply dA dt. And on the right side, pi is a constant, so we could use the constant multiple rule. We have pi times the derivative with respect to t of r squared. Now here, r is a function of t, and so this is a composition. This function of t is inside of the squaring function, so to take the derivative, we need to use the chain rule. The derivative of the outside, that's the squaring function, is 2r, and then the derivative of the inside function, that's r, its derivative is dr dt. And so we end up with the equation dA dt is equal to 2 pi r times dr dt. So there we have it. If A and R are related to each other through the equation A equals pi r squared, then dA dt and dr dt are related to each other through the equation dA dt equals 2 pi r times dr dt. So if we know at any moment how fast the radius of the circle is changing, and if at that same moment we know the actual radius of the circle, then we can figure out how fast the area is changing. In another example, let's say we're interested in a rectangle instead of a circle. So let's say we have a rectangle that has a base b and a height h. Then the simple formula that relates the area to these is area equals the base times the height. And let's suppose that this rectangle is growing. Both b and h, let's say, are either growing or shrinking, or maybe one of them is growing and the other is shrinking. They're both in motion, so that A, B, and H are changing with time, so they are functions of time. So in that case, the calculus expressions dA dt, dB dt, and dH dt will tell you the rates at which these things are changing. dA dt is the rate at which the area is changing. dB dt is the rate at which the base is changing, and similarly for dH dt. So how are these related if the area is equal to the base times the height? So assuming that a, b, and h are functions of time, then differentiating both sides of the relationship a equals bh with respect to time, we have the derivative of a equals the derivative of b times h. So this is dA dt is equal to, now on the right side, in order to compute this derivative, we need to use the product rule, because these are two functions of time, and we're taking the derivative with respect to time. So it's the first times the derivative of the second plus the second times the derivative of the first. And this gives us a relationship between the rate of change of the area and the rate of change of the height and the rate of change of the base of the rectangle. So if at any moment, if you know how fast the height and the base are changing, and if at that same moment you actually know the measurement of the base and the height, then you could use those four pieces of information to compute the rate of change of the area. In fact, if you know any four of the five pieces of information here, then you can figure out the fifth. And in fact, if you knew the area and you knew the base, then the area doesn't show up in this equation, but if you knew the area and you knew the base, then since the area is the base times the height, you could say the height is the area divided by the base, so you would figure out the height from that. So here you need the base and the height to figure out the rate of the area. If the area and the base were given, then you could use those to figure out the height at a given moment. So again, the concept is related rates. If quantities are related and changing with time, then the rates at which they are related, the rates at which they are changing should also be related. Let's look at two more situations, both involving triangles. One example involving the Pythagorean theorem, and another example involving an angle and trigonometry. So suppose we have a point here, and then there's an object moving in this direction, and an object then moving in this perpendicular direction, and we make this right triangle, and we label the sides x, y, and the hypotenuse z. Then dx dt would be the rate at which the object that was moving horizontally is traveling. Dy dt would be the rate at which the object that's moving vertically is traveling. And dz dt would be the rate at which the distance between the two objects is changing. So if an object is moving to the right and another object is moving upward, then z would be increasing and dz dt would be the rate at which the hypotenuse is lengthening. So the obvious relationship between these three variables is x squared plus y squared is equal to z squared. And we're assuming here that this triangle is in motion, and so x, y, and z are changing with time. So mathematically that means we're going to say that they are functions of time. So to find a relationship between the rates of change of x, y, and z, we take the derivative with respect to time of both sides of the relationship. The derivative of x squared plus y squared is equal to the derivative with respect to time of z squared. And here we use the chain rule 3 times, and it's the same form in each time. Each time we have a composition. The inside function is either x, y, or z, and the outside function is the square function. So the derivative with respect to t of x squared is 2x times dx dt. So that might be a little bit unusual. Most of the time we just say the derivative of x squared is 2x. But here, x is a function of time. It's not the independent variable. It's a dependent variable dependent on time. And we're doing derivative here with respect to time. Normally, we say the derivative with respect to x of x squared is 2x. But in our application, x is a function of time, so it's 2x times dx dt. And similarly, for the derivative of y squared, that will be 2y times dy dt. And on the other side, that will be 2z times dz dt. The chain rule. It's the same chain rule applied 3 times, once each for the letters x, y, and z. So there's your relationship between the rates. And one nice simplification, you could divide through by the 2. So you get x times dx dt plus y times dy dt is equal to z times dz dt. So there are 6 pieces of information here. If at any moment in time you know 5 of them, then you can figure out the 5th. In fact, if you know 4 of them, then you might be able to figure out the 5th. Because if you know 2 of x and y, then from the relationship that we started with, you can figure out the other one. So if you knew x and y, and dx dt and dy dt, then you can figure out z, and you can figure out dz dt then from this equation. If you knew x, y, dx dt, and dy dt, then you could figure out dz dt ultimately, because you could figure out z first. X squared plus y squared equals z squared, so you could figure out z. Then you would know 5 of the 6, and then you could figure out the 6th.